Hey guys, welcome back to Food for Thought Physics, where today we're going to be analyzing the motion of an object sliding down an inclined plane. So let's look at the problem first. We have some inclined plane, which is going to be some sort of ramp, inclined at an angle theta to the horizontal, and there's going to be some block of mass m, or some object really of mass m, sliding down this ramp. And the important thing is that this object does not roll at all, it simply slides. So a box of some sort will be fine. And for the sake of generality, let's include some coefficient of kinetic friction between the block and the ramp, which we'll call mu. And the reason we're going to care about kinetic friction is that we're going to assume that for whatever reason, we're going to push this block just a little to get it to start moving, and it's going to be moving the entire way down. So it's not going to stop, but the kinetic friction will continue acting on it in some manner. Alright, now that we've gotten that aside, let's start the problem. First thing we need to do, we need to set our axes. And here we're actually going to set some different axes to make this problem a little easier. I'm going to set one axis going this way, and one axis perpendicular to that going this way. And this axis here, this axis that goes down the ramp, I'm going to call x plus. And this one that's perpendicular to it and going up and kind of diagonally, it's going to be our y plus axis. And we'll see why this is useful in a second. This is actually a much more convenient coordinate system than the regular xy, which is going to be aligned with the ground. So what forces are acting on this block? Remember, in these force problems, we need to first include some free body diagram, which simply is a diagram that shows the various forces acting on the objects. And let's just assume that this ramp here is stuck to the ground, so it's not going to slide around as it might if it were just some object. So first force that matters is gravity. We know gravity is going to be pulling down on this object, straight down, straight toward the ground, with some force mg. And what else is acting on this object? Well, we're going to have some normal force, which I'm going to put here. Normal force is going to be going this way. Remember, the normal force is called the normal force because it's normal or perpendicular to the surface that the object is on, or that a surface of contact rather. So here it's actually going to be this way here, perpendicular to the ramp, not to the ground, and this actually affects the magnitude of this force, which we'll see in a second. So there's going to be this normal force here going up and diagonally. It's actually going to be going in the y plus direction, and we're going to label this as F sub n. And finally, as the block moves down the ramp, as you might imagine, there's going to be a friction force. And the friction force is going to act against the direction of motion, so this way. We're going to just label this as small f, as we sometimes do for friction. Okay, now why do these axes matter? Well, it actually helps us find this normal force and the acceleration down the ramp. So we see, well, our friction force is going to obviously be in the negative x direction, because this object is going to be sliding down the ramp, and the friction is going to be going against that. The normal force is also kind of obviously in the positive y direction, because it's perpendicular to this ramp. The issue here is this gravitational force, is mg, which is not aligned with either of our axes, which means we're going to have to resolve it. So we can resolve this into its y and x components, simply like this. We're going to have some y component going this way, and then some x component, which then goes this way, parallel to the x and y axes. And so, well, what is this angle right here? Well, we see here that this gravity sub y vector here is going to be perpendicular to the ramp, while the mg is perpendicular to the ground. And we also know that the ramp and the ground form some angle theta between them, which implies that the angle between these two vectors is also going to be a theta right here. And now knowing that angle, we can resolve these component vectors easily. We can just say, well, mg in the y direction is going to be some mg cosine theta, and then mg in the x direction is going to be some mg sine theta. So now all of our forces are going to be aligned with our axes, which makes the analysis a lot easier. First of all, we see that this F sub n needs to have the same magnitude as the gravitational force, because the object, you can imagine an object sliding down a ramp, is not going to be going in the y direction here. It's not going to be moving this way or this way into the ramp. So we know that our normal force is going to also be equal to this mg cosine theta, in magnitude that is. Let's figure out what friction does here. We know friction force is going to be equal to F sub n, the normal force, multiplied by the coefficient of friction. Here it's going to be the coefficient of kinetic friction, which is mu. So we can plug in this F sub n that we just solved for to get that the force of friction is going to be some mg mu times a cosine theta. And now we see, well, the y forces cancel out, so there's no acceleration in the y direction. But what about the forces on the x-axis? Well, on the x-axis, we're going to have some, let's see. It's going to be, let's first set this net force, this mass times acceleration in the x direction, that is. This is our net force, and what is it going to equal? Well, we see that this gravity, this mg sine theta in the x direction is going in the positive x direction, so we're going to include that first. So we have mg times sine theta. And then in the negative direction, we're going to have this friction, which we calculated as mg mu cosine theta. So we're going to subtract that, minus mg mu cosine theta. And now we see, well, if we divide by m on both sides of this equation, we can just get a sub x, acceleration in the x direction, is going to equal g sine theta minus g mu cosine theta. And, you know, we can factor out the g or something, make this look maybe a little nicer. Well, once we calculate this, we can get our velocity and our position functions really easily just with our constant acceleration derivations. We're not going to do this here because there are way too many terms here. But, well, let's see what happens if we have no friction. So this is the general case with some friction mu. But if there's no friction, a more idealized case, then we're going to get, let's see, so if mu equals 0, that implies that our acceleration is going to become, this term entirely vanishes, so it's just going to be now g sine theta